Hello. Welcome to our third Rust KW Meetup. Today's speaker is Sid. He'll be talking about graph mining in Rust and his experiences in new Rust Station. After that, there will be hopefully 3 demos, each about 5 minutes long. Thank you for Sortable for providing us with hosting and pizza.
Alright, let's get this started. So I learned Rust very recently for this graph mining project actually, and I was very excited to learn it, and then I jumped at the opportunity to actually speak at the Rust KW Meetup. Thank you for that. And this is a perfect opportunity to lure you in and then listen to my rambling on how I got excited on Rust and so on. So let's get started. Alright, so this talk is divided into 2 clear sections. So what brought me to Rust. So I'll talk about the graph mining project that we had to do and how I ended up using Rust for it. And the second part of the talk will focus on why I am thinking of sticking to Rust, right? And what made me love Rust and think this is a really good language to program. So we'll see. Okay, so the project was on mining graphs, and specifically, given a graph, we wanted to mine subgraphs out of it, right? So for example, if you have a graph with just 3 nodes, so it forms some patterns, right? So these are all possible 3-node undirected subgraphs, right? So there's the unconnected open triangle is what we call it, and this is a closed triangle. And we wanted to say that given a graph, give me the count of all such 3-node subgraphs, right? So that's what we're trying to mine here. We wanted to see the distribution of these subgraphs in any given larger graph, right? So for example, if you have this graph data, so this is your actual graph, let's say, and these are the patterns we are looking for. So if you actually go and count them, you will see that there are 8 open triangles in this graph, so I can enumerate some of them, 1, 2, 3, 4, and so on, right? And there are 8 of them. Similarly, there are 2 closed triangles in this graph, you can easily count them. So once you have those counts, you can easily see the distribution is 0.8 and 0.2. Right? So that's the probability of finding the subgraph in this large graph. So this is exactly what we wanted to find, this distribution. And we wanted to find this for 3, 4, 5 node subgraphs. So let me give you another example. This is all possible 3-node directed subgraphs. Right? So the earlier one was undirected, this is directed. So this is the arrows pointing outwards, arrow pointing in one direction, and so on. Right? So these subgraphs have direction. And then given a directed graph, you want to again find the distribution of all these subgraphs in this larger graph. So again, to give an example, if you count this, there are 1, 2, 3 such subgraphs in this larger graph. So these are the counts you get. And once you have all the counts, you can find the subgraph distribution. So in this case, the graph is really small, right? So you can actually go and count them. But imagine that you have a graph with a billion edges. So actually going and querying all these subgraphs one by one, or even in parallel, will take a lot of time. That's a huge computation you have to do. But there are some very nice tricks to actually estimate this subgraph distribution without actually having to count it. So one such technique is, alright, so before I tell you about the technique, so this is a very interesting series that I found. So I wanted to check of how many subgraphs are possible for a particular k-node subgraph. Right? So as we saw, for undirected 3-node subgraph, there are only 2 possible such subgraphs. Right? So if you see this series, so there are 2 3-node undirected subgraphs. Similarly, there are 6 4-node undirected subgraphs, and so on. So this is a series. And as you see, it grows big pretty fast. Right, because the possibilities increase as you increase the number of nodes. Similarly, this is the number of directed k-node subgraphs. So as we saw, there are 5 possible 3-node directed subgraphs. Then there are 34 4-node directed subgraphs because, again, there are a lot of possibilities. So this is a pretty cool series if you want to keep in mind. Alright, so the technique that I used was in this paper. It's a bioinformatics paper. And this one essentially gives you an algorithm which you can use to estimate these subgraphs given any graph, any large graph, right? And the algorithm is pretty simple. You first load the graph, and you essentially, so this is sampling the graph. So instead of actually going and counting all your subgraphs, doing an actual count, you sample it n number of times, right? So that's essentially estimating it. So repeat it n times, you sample one subgraph from G. So you go and pick 3 random nodes which are connected somehow, and then you see what subgraph you got. So this could be, like, say, the open triangle or the closed triangle, right? So once you sample 3 nodes, and there is some probability computation here to eliminate bias, which you don't really need to go into in details. But the important point is, once you have the probability, then you do some calculation, and at the end, what you get after n sampling is you get the distribution of these subgraphs. Right? So you don't really need to understand how the algorithm is working, but this is the general flow. Load a graph, do something n number of times, sample subgraphs, calculate probability distribution, and so on. Right? So that's the general flow. All right. So take 1. I started doing this in Python, right? So Python is very easy to get started with. Like, if you want to prototype a system, you just write, you declare variables, you create a structure, and then you get going, right? No need to think about all your data types and so on. So, like, that's the advantage of dynamically typed language, right? So that's my setup. I downloaded some graphs from Snap, Laboratory of Web Algorithms, Connect. These are essentially collection of graphs that you can download from the web. And I set up Jupyter, because that's really easy to actually load the graph in one cell, and then you work with that repeatedly. Right? So Jupyter allows you to interactively work with large graphs. So you can load it once, and then you can keep querying it and so on. So that was my setup, which was all fine. It was good. Alright, but so this is what happened. I loaded a graph called Web Notre Dame. This is a snap graph, which is not very large, like 32.3 million vertices, 1 million edges. Right? It's pretty small graph, relatively. And so this is, I'm doing 3 computations, or 3 sampling. I'm trying to sample 3 kind of subgraphs. So 3-degree undirected graphs, 4-degree undirected graphs, 5-degree undirected graphs, right? So that's what I'm trying to sample, the distribution of in this big graph. And as you see, I'm sampling 64,000 times. So in that loop that you saw, I'm doing that for 64,000 times. And my throughput essentially is 10,000 for 3-degree undirected. Right? So that many samples I can do per second. And this is Python. But as you see, as I increase the number of nodes, my throughput decreases a lot. So from 10,000 it decreased to 4,000 and then 500. Right? And this is after I had spent some time actually trying to optimize the code. So this was like 3-degree iterations and so on. So I did see what are the hotspots trying to eliminate, and after that, this is what I got from performance. Now, of course, there would be a lot more improvements to do in the Python code, like I'm sure. But so this is where I had stopped. This is similarly for the directed graphs. Again, 10,000 and 4,500. So those are the throughputs that I was getting from Python. Similarly, I tried to do it on larger graphs. So that was just 1 million edges. So there are even larger graphs that you can download. This is from the Laboratory of Web Algorithms. And so there are 2 graphs that are downloaded which had 1 billion edges and 3 billion edges to actually, like, again, get the subgraph distribution out of these large graphs. That's what we were interested in. So one problem that I also started facing is loading this graph itself. So the first step of my algorithm is to load that graph. Right? And these graphs are essentially in the form of CSV files, like text files. So you have to first load the graph into some data structure that you have created, and then you can get to work with your graph. So as you can see, for loading 1 million edges, I was essentially taking around like 5 seconds per million edge. And this is really slow if you want to load a billion edge graph, right? So you have to wait for around like 20 minutes, you have to wait for loading itself, and then you start querying your graph. So that's really slow. Another problem that I faced was out of memory errors. So even in server which had 200 GB RAM, I was getting out of error. The Python processor was going out of memory because I was trying to load the 3 billion edge graph. And like partly it is my fault, my data structure was not that optimized in Python, the graph data structure that I was using. But Python data structure itself take a lot of memory. Like one Python integer is 28 bytes, right? Just to store one, you have to take 28 bytes. And that like essentially scales as you start loading a billion edge graph. So that's a lot of memory. So I thought that instead of trying to optimize Python itself and trying to fight with its memory requirements and so on, I would move to something else, right? Some other programming language. So take two was Java. So I'm a PhD student. I work at the University of Waterloo, and we developed a graph database called GraphFlow, and that was in Java. That's what we started off with. So I had like essentially experience in building graph systems in Java. So that's my take two, like natural thing to do, right? So I just implemented the graph loading code. I did not want to implement the whole thing before testing if it's working properly. So I just implemented the graph data structure and the loading code. So take a CSV and load it into the graph, right? And these are the times I was getting. Like 0.5 seconds per million edge. And that's like so good. As compared to 5 seconds per million edge, that's nothing, right? So this is like very fast. So you can see how Java is helping you give this performance as compared to Python. This is pretty good, but in between, you get these 21-second time loads, right? And you can guess what's happening, right? Garbage collection. And 21 seconds still seems fine, right? I mean, 21 seconds at 41 million edges is still fine. But as my count increased, as I reached the 1 billion edge count, these pauses were going up to 100 seconds or even larger, right? And that's, I mean, it's understandable because as my data structure is increasing, it has to resize and so on. And then it stops and does garbage collection, right? Now there are ways to deal with it. I do not want to do it, right? So we had faced these issues before, and I was like, I don't really want to deal with because I just want to get on with my subgraph mining project, right, and not deal with garbage collection issues. And at the same time, like in parallel world, I was playing around with Rust. So I was trying Rust on exorcism, like reading the tutorial and so on. But I never really like got off on learning it. Like I knew the syntax, but I never really built something on it. So those two came together, and I was like, all right, why not learn Rust and do this project together, right? So take three was Rust. And so in this talk, I'm not really showing any code, so I'm just telling you about my experience. So there's no code thing that I'm going to talk to you about, right? But I just want to show you how it gave me that performance that Java was giving, but without those problems. So this is, the loading time is Rust. You can see again, it's 0.5 seconds around per a million edge. And this was like the first code I wrote. The first code that compiled, and this is what I'm getting. So this is, I'm sure there are again optimization improvements that I don't even know about, right? But I'm getting pretty close to Java performance in the first code that I wrote in Rust. That's pretty good. And there's no garbage collection. So this is maintained throughout until I load all the billion edges from my file. And that was really cool. Similarly, after I'm done, so I ran the subgraph mining code, so I implemented the whole thing in Rust. And you can see the throughput I'm getting is very, very large as compared to Python, right? And that's consistently very large. So I could even go up to higher sampling rates. So I could go up to 512,000 samples and so on. So taking my code, taking my project and implementing in Rust actually helped me get the performance that I was looking. So that's pretty cool. Feels so good. So after looking at the Java garbage collection pauses and looking at the consistent 0.5 second loading time in Rust, that was the exact feeling I had. Okay, Rust is pretty cool. So that essentially sold me Rust, right? Alright, so that was part one of my talk. So that was my experience and how I got started with Rust. So in Python, you can do rapid prototyping, but then it's very easy to forget the data structure sanity. Because it's just very easy to willy-nilly create any data structure you want, you actually forget your memory requirements, which happened to me. I mean, there are ways to be very disciplined on it, but that's what I faced, right? Java, you get the high performance, but then you do have to deal with garbage collection, which is, again, something you have to worry about and think about. But then Rust has high performance, and what I found and what like the community itself keeps saying is once it compiles, it will probably run fine. Right? So that's a very high guarantee that Rust is giving us, which is pretty cool. Alright, so that was part one. Part two will be about what's keeping me fascinated. Yeah.
Some questions.
Sure.
So did you test Java performance or just loading the graph?
Just loading the graph. Like I didn't even implement the other code. That was just the loading and the graph structure.
And you mentioned GraphFlow.
That's right.
What's that? It's an open source tool? Or?
That's an open source tool, yeah. That's on GitHub/GraphFlow.
I missed what's for?
It's a graph database, so we built this from scratch. And our main, so it was a research project. So it's not like, it's not fully built and engineered so you can put it in production. But one of the cool features in that is, so the subgraph queries that we are doing, right? So looking for triangles in the, they are worst case optimal. So that's one thing that we focused on. So let's say you take a relational database like SQL and you try to find triangles in it. So you can do that. You can join, you can have a table which has edges, and then you can join it 3 times to get the triangle, right? But the joins there are binary joins. So what our contribution is to implement joins like that, but using worst case optimal algorithms. So that was our project.
And you mentioned this open source graphs or something, databases of graphs, yeah?
Yes, so they are graph data sets.
How you import them, in what format? I don't know if you mentioned.
So most of them are in CSV format.
Oh.
So just like ID space ID or something.
And your implementation use the same data structure in all languages?
In Java and Rust, yes. So the Java and the Rust were the same. In Python it was even worse data structure. I don't want to talk about.
Can you share what method you use to represent the graph?
Right, so it's a sorted adjacency list. So if you have a directed graph, you have essentially a huge array which is representing all the vertices, and then each vertex is essentially a sub-array which is representing its edges or its neighbors. Yeah, say index-based graph structure.
So this is the optimal method to represent graph?
Given what queries you want to do. So if queries like subgraph queries and path finding queries, they are, as far as I know, they are very efficiently done with adjacency list. But there are other graph algorithms where you can probably get better performance with matrix form. But I have not really worked with them.
Thanks.
Yeah. Alright, so part 2. So this is essentially like a whirlwind tour of what I found fascinating with Rust as I developed my program. So there are 2 aspects to this. One is obviously the technical aspect, that's very fascinating. But there's also the social aspect, which I will talk about at the end of the talk. So 2 core technical things that Rust gives us is, one, the borrow checker, right? And as soon as you start learning Rust, you will find this term, right? And as soon as you find this term, you'll be fighting this. And why is that? So a key contribution of Rust is it helps you give a similar coding environment that C, C++ gives you, but it helps you avoid manual memory management, right? So Java does the same, but the way Java does is it has a garbage collector that's essentially managing the memory for you. But in Rust, they also wanted to have no garbage collection, or that's what they call a minimal runtime. So the runtime cost should be very minimal from Rust. And combining these 2 ideas, you don't want manual memory management, but you want a higher level paradigm than C, C++ is giving you the borrow checker. And the idea is pretty simple. Any object that's in memory or any data that's in memory in Rust is always owned by one object, always owned by one variable. Like let's say you define let graph equal to new graph, if borrowing Java terms. So that graph variable will always own the graph object, right? And the only way you can give it to others is either you give it totally and then you relinquish control over the object, or you pass a reference to it. And those references are kind of two types, right? One is a mutable reference and another is an immutable reference. And what Rust enforces is there can be multiple immutable references or read-only references, but there can be only one writable reference to an object at the same time, right? And this is essentially kind of a locking system where there can be multiple reads but only a single write. And you can see that here, what's happening is I have created an object, right, which is Meetup, and this Meetup essentially now owns this object. And later I'm creating a reference to Meetup, and this is a mutable reference, so I can edit it, and then I edited the location, right? And later, at the end of the code, I'm trying to print it. So what Rust will do is give you an error in this case, because this variable has a writable reference to your object. So what Rust says is that object might edit this object anytime, and so it's not safe to read. So this one is not allowed, right? So currently, how to solve it is you just put this inside curly braces, or like put this code in a new block. And what Rust does is, as soon as the block ends, it deallocates any variable that was in that block automatically. Yeah?
Is the reference that you're printing at the end actually supposed to be Meetup?
Can you repeat that?
At the end you're doing print line, reference.prettyprint. Is reference there supposed to be Meetup?
Yeah, that's correct. Yeah. Yeah. Oh, that's sorry. So right. So this one should go away, but you want to try to access Meetup again, essentially. I'm sorry about that. Right. But what Rust does is, again, as soon as the block ends, it automatically deallocates any variable that there is. So the reference goes out of scope, and then so this will be Meetup, and then you can access Meetup again. Right. And this is a very simple idea, which leads to very powerful paradigms in Rust. For instance, what they call fearless concurrency, right? Because they can ensure that any object has at the same time only one owner and or only one read reference, one write reference. So it can like make your code concurrent very safely. Right? And in C++, you might have to deal with a lot of issues where you are not sure whether you can access a memory pointer, right, across different objects. All right. And the second thing that is very cool in Rust is the functional paradigm. And so Rust aims itself to be a systems language, so it is more in the area where C++ operates, but I like to think of it as more Haskell in disguise, right? So it has, the focus is on system language, but the language features that it's developing is like a lot of that is borrowed from Haskell world or functional programming languages world. And all that is done with the minimal runtime that I mentioned earlier. So they try to do that without having a lot of runtime cost. And there's also something called zero cost abstraction. So you can add features to Rust, but they should not be affecting programs that do not use those features, right? And I'm not going into details of how they are implementing it, but that's what their core focus on. And this is one example of a functional feature that Haskell, I've seen in Haskell, which is called type classes in Haskell and called traits in Rust, right? So what's happening is this function has a generic parameter t, which you might have seen in Java or C++, right? But it also has a condition on that parameter, which says that this generic parameter can only be of type summary. So you're essentially limiting the kind of objects or kind of types that can be instantiated for this function. Right? And this is kind of similar to Java interfaces, but it's a lot more powerful. Alright, so one other cool feature that Rust is, as I think it has taken a lot of learnings from other languages, and it has built a lot of tools around the language itself that it kind of says that you should use from the very beginning, right? So in C++, you don't really have a build manager or build tool. So you learn C++ and then you learn make or CMake or something, right? In Rust, they have already built these tools around the language itself. So there is Cargo, which is the build manager in Rust, and you will probably always be using Cargo anyway, right? So you will not be calling the Rust compiler yourself. You will probably always be using Rust. Cargo. Similarly, there's a tool called Rustup, which is essentially allowing you to download different versions of Rust. So Rust has stable, beta, nightly, and you can essentially use Rustup to download any version, play around with it, and it's very easy. You don't have to worry about getting a package manager to install Rust. There are two other things that I find they're still not stable. They are still in nightly stages. But there's the Rust format and Clippy. So Rust format allows you to format your code automatically, and Clippy will point out small mistakes that are not syntax errors, but might be logical errors, like if you're casting a 32-bit integer into a 16-bit integer and so on. Right? That could be something you might don't want to do. So Clippy will point out to that. And that actually happened to my subclass discipline code, where I was casting a 32-bit, 64-bit integer into a 30-bit integer without even realizing. And Clippy pointed that out to me. So given these tools, so Rust format is essentially saying the Rust ecosystem kind of should have the same format of the code throughout the ecosystem. So any Rust code that you read will probably read the same to you. So that's kind of having a opinionated community around the language itself. Right? So they are saying, okay, this is a format which Rust will follow, and if the whole ecosystem follows it, there's a certain stability to it. Right? And crates is essentially what a package is in Rust, and any program that you build will probably depend on other crates, which are essentially packages. Alright, so there's a very extensive documentation. The first thing that you will probably go and read is the book, is the Rust programming language, and this is like a really good starting point if you're starting Rust. So that's the first place you should go. And there are some other books that, for instance, Rust by example, it will give you small code snippets to actually see how the program is working, right, or how to get started. And there is a larger book that's being written right now. It's not yet stable. Is Rust Cookbook, and it essentially has the same, like some recipes to build general programming tools that you want to build. If you want to follow what's happening in Rust, This Week in Rust is like a weekly newsletter, and it gives you all the things that are happening, new blog posts, new features that are being built in Rust, and so on. So that's something that you really want to follow if you are interested in Rust. And there is a wider community around this whole thing. Alright, so I wanted to talk about the code that I just showed you. And so if you notice, the reference that you created, you only used it once, right? And you might not have used required reference again, and they should again be meter, right? So this seems a bit silly that the compiler is complaining that you used it once, but you still have to worry about using it, like affecting it in the later part of the code, right? So they are building something called non-lexical lifetimes. So right now the lifetimes is how it is used, is at the block scope. They are trying to reduce it to these scopes. So if you define reference, use it and never use it again, it will compiler will not give you error anymore. And this is a feature that they are currently working on. Some other features that I'm pretty excited about, that I've been reading about, async await for asynchronous programming, and this will lead to, in the future, features called generators, which you might have used in Python, right? So you might have a function and you can yield a function, and it will not execute immediately, it will execute each time you call it, right? So that's a very easy way to create an iterator without taking a lot of memory, having to allocate everything in memory at first. Alright, so I'm not going to go through all of them, but these are some cool features that are going to come in Rust, and that I'm pretty excited about. Alright, and the way you introduce new features in Rust is through request for comments, and that's totally based on GitHub. And why I'm mentioning this is because it's pretty active right now. A lot of features are being built into the language. But what's more exciting is to see the decision tensions that happen per feature. Right? So you want to introduce a feature, let's say, how to improve the module system in Rust, right? How to improve the package system in Rust. And one person might have one idea, but then 3 other people will come and say, hey, that idea has these problems A, B, C with it. Right? And if you go through all those comments, you'll actually see how ideas are being generated, commented on, refined, and then in the end you get a really good product that is kind of like a merging of all the good ideas in the comments. So I find that pretty exciting, and some of the features that are currently being introduced, like non-ASCII identifiers, some of them get a lot of comments because a lot of different people are interested in their own kind of features that they want in the language, and then the volume of the commenting gets a lot. Yeah.
Do you have war flames? I mean, people.
I'm going to exactly talk about that in a bit. All right. So having said that, the RFC process and a lot of people coming together to discuss features in a language will lead to war flames. Right? So, like people will want to enforce their own ideas of how something should work. Someone will say no, and then they get heated arguments. What's awesome about Rust, and this is the social aspect that I was talking about, is so they have a code of conduct, right? And they say we are committed to providing a friendly, safe, and welcoming environment, right? Which is kind of taken for granted, right? So any community that you build probably should have these goals already. Right? And then they also say, please be kind and courteous. There is no need to be mean and rude. Right? So this is something that's probably already expected in any community. What I find amazing in the Rust community, these are enforced very well. So when I was starting my sublab project, I went to Reddit, obviously, because I wanted to solve some problem and someone had already asked it. Right? And in one of the answers, someone was being mean. No need to be mean or rude, right? So in some sense they were being mean. And what I found amazing is, someone replied to that, answered the question and said, you don't really have to be mean, right? And that was something that I noticed a lot of times in many different interactions in and around this community, which I've probably not seen before. So this sense of being welcoming and being nice is actually